Today we're going to take a look at section 4.1, which is titled Antiderivatives. And before we actually do antiderivatives, what I want you to do on the front page of your notes is I want you to fill in all the derivatives that you know. And you should know all of them, but if there's one that you've forgotten, maybe it's a trig one or something, that's cool. You're just going to write down what the derivative is next to the function. So in other words, on the first one, we'll just do the very first one together. What is the derivative of y equals b if b is a constant? 0. So write it appropriately. So this is going to say y prime equals 0. Or if you want, you can write dy dx equals 0. So I want you to go down this list. Write down all the ones that you can think of in the right, proper way and all that good stuff. After you've done that, turn to a neighbor. Most of you are close enough to somebody you can turn to them and just check and make sure that you have the same thing written down. Okay? And then we'll regroup and make sure everybody has the same thing as a class as a whole. Okay, Allison, you're going to fill in the first one for us. Well, I filled in the very first one, the constant multiplier rule. The next one's a linear function rule. Okay, so we have the linear function, something like y equals ax plus b.
How do you write?
You need to flip that around. It has to be this cushion side.
Oh.
It's that touch sensitive. It's like your phones, right? Your cell phone. It only works with your fingertips. It's kind of like that. All right. Does everybody agree with Allison? That one look good? Fantastic. Thank you, Allison. All right. Alexa's next. We have the constant multiplier rule. This one's one that we use all the time, but it's a little bit funny to write down.
Oh, that looks horrible.
So y prime equals...
Okay, I couldn't tell what this one was asking. Is it
You're
k?
just trying to run the derivative. It's k times the function
Okay.
f of x.
Wait, how do I... Oh, I did not get myself enough room.
Write down what you think it is, and we can help you fix it if it's not quite right. All right, do you guys agree with Alexa? I agree with her too. Very good. All right, so we just take the function's constant multiplier k, and it just carries along, and we take the derivative of whatever the variable part is. All right, Mackenzie. The sum difference rule. You have to use the cushion side of the stylus. Don't break the iPad. The IT department will not be happy with if I do that. Okay, do we agree with Mackenzie? Does that look good for the sum difference one? Wonderful. Okay, let's pass it back. Andrew, your turn. Power rule.
Con lo otro, creo.
Y equals x to the n.
Ah, yeah.
So your job needs to be to show the next person how to write with the stylus. We'll do that. Okay, power rules. Does that look good? Everybody agree? Great.
I have to write something else, but no how.
There's nothing else to write. What else did you want to write?
The prime of... the derivative.
Oh, the derivative of the x value?
Yeah.
We do have to do that when we're doing like implicit differentiation, but if our function is a function of x, then the derivative of x would just be 1.
Okay.
So we don't have to have that piece actually. All right, let me switch to your next slide. Okay. All right, we're on to the trig rules. Oh, goodness. All right, Daniel's got y equals sine x. He thinks that y prime equals cosine x. What do you guys think? Is that all good? Awesome. Okay, so Josh, you know which side to write with?
Mm-hmm.
Great. All right, next one. Josh is going to take a look at y equals cosine x. Do we agree with Josh? Is that all good? Excellent. Snyder. Y equals tangent x. Mr. Snyder says the derivative of tangent is secant squared. Does that look good? Excellent. Why don't you pass it back to Jacob next? We've got exactly the right number of people. It's almost like I planned that. Wonderful. Jacob's turn. Secant x. These are the ones we see less frequently, so let's see how much we remember these. Derivative of secant. we do. Oh, somebody's not going to get to write. Oh, that's a bum. Stephen, you don't want to write? Okay. All right, Jacob, go ahead and pass that one over to Cooper either way. Okay, did everybody agree with that? As secant x becomes secant x, tangent x will take its derivative? Great. All right, cotangent x. Does that look good? Negative cosecant squared. All right, great. We have one last one.
Go ahead.
Steven says he doesn't want it. You've got it.
All right.
Last one.
This side you say?
Cosecant x.
Which side did you say it right
The
with?
squishy side. Yeah, that's the
That's
one.
it? Oh.
Uh-huh.
How do you scroll down?
Watch. All right, if we put a y prime in front of it, it would look like the other ones. Does that look good? Negative cosecant x, negative cosecant x, cotangent x. All right, so these are rules that we've been using now for probably about 2 months almost, right? Not all of them for the whole 2 months, but we've been working on this kind of an idea for 2 months, okay? All right, so what I want to do is I want us to flip to the next page and take a look at what we're going to do now that we have remembered or have thought through these one more time. Notationally, what we're about to do is to set something up to give us the ability to write antiderivative, kind of like we wrote derivative as y prime. So capital F is going to be an antiderivative of a function little f on the interval I. The indefinite integral of f of x with respect to x on the interval I is defined by, you see this sort of tall, skinny S shape? You see f of x, there's that dx, you've seen dx before, equals capital F of x plus c. And we're told that c is an arbitrary constant called the constant of integration. So let me start with what's going on with the c at the end, because that's perhaps the most awkward part of what's going on. I want you to think about two functions. I want you to think about the function y equals x squared. You know what it looks like. And I want you to think about the function y equals x squared plus 3. What does the plus 3 do to the graph of x squared? It just moves it all up 3, right? What happens when you take the derivative of both of those functions? It's the same thing, because derivative is about the shape of the graph, not the location of it really, right? It's the shape. All right, so this plus c on the end is recognizing the fact that when we go backwards, we have the ability to shift something up and down, and it doesn't affect what the original functions started out as, okay? So that's what the plus c is doing. It's allowing this possibility of this shift to go on. That's all that is. That said, when you take an antiderivative, you need to make sure that you put a plus c on it, all right? So when you take the antiderivative quiz, in particular next Thursday, if you miss the plus c, what do you think is going to happen to the problem on the quiz? It's wrong. And I will tell you, the very first time that I gave the quiz at OBU, and it was a version of this quiz, it's not exactly the same one, but it was a version of that, I had a student get every problem right, except on every single problem he did not put plus C. Every single problem. Which meant that his score was recorded for the first time as a 0, he didn't get extra credit, okay? So please, please, please remember the plus C is going to be important for what we're going to do. Now there's going to be a couple occasions, I can't remember which section it is, where we're going to actually find out what that C value is. We need additional information to have a C value, but that will happen later. So for right now, we're going to have a plus C on things. This notation, this script S, is like saying, I want to do the derivative backwards. I want to go backwards. Okay, so what we're going to do next is we're going to take that same, basically, that same list of derivatives, or the same list of functions that we did before, and instead of going sort of forward in finding the derivative, we're going to go backward and find the antiderivative. That's our goal. So I'm going to help you with that so you can kind of see what would happen. What we want to think for right now, until we get into the habit of doing it, is what function would have had a derivative of 0? That's our first one here, right? Y equals 0. So what function would have had a derivative of 0? A constant function, right? So I'm going to use, and I know that some of your y's don't look any different when you do a capital versus a lowercase. But what the notation is that we capitalize what was previously lowercase. So this is a lowercase y, so now I use a capital Y. If it was a lowercase g, I'd use a capital G. If it was a lowercase f, a capital F. Okay, that's the notation that is accepted to use. So I'm going to use capital Y's in all of these. And a constant is what we have. So you can write a constant k. You could write a constant. We'll use c since your book keeps using a c. That's what I've written down in my notes. C. So anything that I would have had a constant of, if I took the derivative, I would get 0. So if I have a derivative of 0 and I want to go backwards, then I would get a function that was a constant. Make sense so far? We're all just thinking backwards. Next one, y equals k. How do I get a constant when I take a derivative? Well, I would have had what? Okay, so it had something like, I think you're saying kx like this. And then what do I need on the end? I need a plus c. What is this kx plus c an equation of? A line with a slope of k, right? So how do I get a constant derivative? Well, I had a line to begin with, a slope with a slope of that constant value, which they called k in this problem. Constant multiplier. What do you think you're going to have to do? The constant multiplier rule of taking a derivative does one thing. What do you think is going to happen when we do the antiderivative? Just guess. What do you think is going to happen to the k at the beginning? It's just going to be the constant in the antiderivative as well, just like it was for the derivative. So when I took the derivative of a function, f of x, I got the derivative there. If I do the antiderivative, same thing. So it's capital F of x. So I just do the antiderivative of the variable part. That's what that's saying. And then what do I need? Plus c. And if you think algebraically about these derivatives, what happens when these plus c's on the end? What happens if I took the derivative of capital Y equals k, capital F of x plus c? What happens to that c on the end when I take the derivative? It's 0, right? It goes away. So that's why we're putting that plus c in there as well in terms of, does it undo itself and become 0? Yes, it does. What do you think would happen for the sum difference rules? Same thing, right? If I've got a sum or a difference, I just take the antiderivative of each piece of it. That's very handy. Notice that's a sum difference issue. That's not for products and quotients, right? Just like with products and quotients for derivatives, it wasn't quite that simple and clean to just take pieces of products and multiply them. Can't do that. Can't do it for antiderivatives either. All right, now here's the first one that's the most interesting. Everything up till now has been rather uninteresting, to be honest. This one's interesting. Let's think about, what did you do when you took the derivative of x to the n? What did you do with n? You brought it down in front, and you did what with that n? Well, you did for the exponent you did, but what did you do? What did the n in front do? It was multiplied, right? So the exponent was multiplied by what comes next. What's the opposite of multiplication? Division. We're going to see division happen here in a minute. Okay? Opposite of multiplication is division. The exponent, you mentioned, Snyder, the exponent was decreased by 1. What's the opposite of that? Increased by 1. So we're going to see an increase in our exponent. Here's the other thing that we probably wouldn't have put together, and so I'm going to just tell you, is that you used the original exponent n and brought it down, right? And then you decrease the exponent. We're going to do it in the other order. Basically, we're going to increase the exponent first, and then we're going to use that as the value that we divide by. So what this ends up looking like, capital Y, equals, I increase my exponent by 1, and then I divide by that exponent instead of multiply. And then I've got a plus c, which I definitely missed on my last problem, didn't I? Let me move that in there. There should have been a plus c. Please make sure you put that plus c back on the sum difference rule. I left it off accidentally. Man, we all have our moments, right? Where we forget things. Okay. All right, so again, let's talk about the power rule. Instead of decreasing the exponent, you increase it. Instead of multiplying, you divide. Instead of multiplying or using the previous exponent, you use the new exponent in plus 1. Now think with me about this. This is an interesting one, right? If you were to take the derivative of this new expression we have over here, and you took the derivative, you'd say, okay, you take the n plus 1 and you bring it down, right? What would happen to the n plus 1 that you brought down with the denominator? It would cancel, right? And you would decrease the exponent by 1, and what would that become? N plus 1 decreases by 1. What do you get? N. So it does, in fact, turn back into the x to the n, right? You should be able to unthink it to make sure that it really works when you're processing through these. And, of course, the plus c on the n turns into 0. Okay, let's take a look at another set. You'll notice a few things on this one. What you will notice is that these are not the trig functions sine, cosine, tangent, secant, cosecant, cotangent, is it? That's not what it is. It actually looks an awful lot like the derivative side of this list, doesn't it? It looks like I've taken that stuff that's in blue and I've made my list out of that instead. And that's on purpose. We'll actually get derivatives for the other ones that are missing later. But right now, our purpose is to use what we already know and to reverse it. And this is what we already know. So this is where we're starting on this, okay? Now, the derivative of sine is cosine. So the antiderivative of sine is also going to be cosine. But what do you think is going to happen? What's that? It's going to be negative. The sign is going to be opposite. Plus c, thank you. Okay, so the derivative of cosine is, it's negative sine x, isn't it?
Oh, yes.
Yes. So the antiderivative will also be sine x, but now it will be positive. So you get the opposite sign that you would have gotten with sine and cosine when you do the antiderivative. So to be very honest, there's only one of the trig rules between the sines and cosines and the derivatives and antiderivatives that I remember. I remember that sine of x derivative is cosine. That's the one that's in my memory. It's the one that was ingrained in me when I was in a Calc 1 class myself. And then, remembering that, I can figure out what all the other three would have to be. Am I doing an antiderivative or am I doing a derivative? Is it sine or is it cosine? Because everything else just builds upon that. If I remember that derivative of sine is cosine, then I can figure the rest of them out if I need them. That's the one I remember. Secant squared. Whose derivative was secant squared? Tangent. So the antiderivative of secant squared is actually tangent of x plus c. Whose derivative is secant x tangent x? That is secant of x plus c. Cosecant squared. Yeah, it's the opposite sign. Very good. And it's what? Cotangent, right. So the opposite sign, because the derivative of cotangent was negative cosecant cotangent, right? I'm sorry, negative cosecant squared, right? Looking at the wrong line. So the opposite sign happens. How about cosecant x cotangent x? Yeah, and is it positive or negative? It's negative. The derivative of cosecant is negative cosecant cotangent. So the antiderivative of cosecant cotangent is negative cosecant x. Okay, so as we're working today, keep that list handy. You're going to want it. We're going to do quite a few examples. That's the idea, okay? And not only are we going to do some examples, but I want you to know that while your book gives you some examples, I mean, like it does a lot of problems, and that's great, it's certainly not, like infinitely many things to practice on, especially for the quiz that you're going to do next week. So online, you'll see that I have posted a section from another textbook, basically the same thing. It's even 4.1, which is interesting. So 4.1 from another textbook. And all it is it has a lot more problems to practice on. Okay? Not only is this posted, but the solutions for it are also posted. Okay? So you've got more to practice with. Yes?
We won't have to like simplify on
No, you do not need to simplify on the quiz. But on the homework, you will. Yes. Just like when we did the quiz before. The idea is this. I want to be able to test to make sure that you know the rules and how to apply them. And that's what the purpose of the quiz is. Your homework prepares you for the test, which actually involves a much bigger scope of what's going on, which is know and apply the rules, and then use the algebra, that's the prerequisite kind of for this class, to actually be able to clean things up. So it's a way of testing both things without, separating the testing of those two things, basically. All right, so let's do some examples. You'll notice the notation has that script S in front. So when you see that notation, it's telling you, take the antiderivative. Okay, so even without the directions at the top that says find the general antiderivative, that script S tells you that that's what you're going to do. All right, so let's take a look at this piece by piece. I've got a 2x. So in reality, the 2 should stay. What happens to x? We increase the power. It's currently a power of 1, so I'm going to increase the power to 2. And then what do I have to do? Divide by the new power. Now that's going to simplify with the 2 in front here in a second anyway, but that's what happens. How about that 3x squared? Well, the 3 stays. What happens to the x squared? X to the third, and then divide by 3. And then I need plus c. Every problem will have that plus c on it. And like I said, there will come a point where we're going to figure out what c is in certain situations, but for now, it's always plus c. So if you were doing the quiz on Thursday, next Thursday, you could stop right here, right? Totally fine. For what we're doing, it would be silly to stop right here. This is a very simple cleanup, and this is something that's going to make the problem look a lot nicer and easier to work with when we're working with them. So we're going to reduce the 2 here, and we're going to reduce the 3 here. So this problem ends up being x squared minus x cubed plus c. Now here's the cool thing. I know I just told you that I posted solutions to something online. And I know that for the odd problems in your book, you have the back of the book and you can check your answer. But can you not check your answer here anyway? You should be able to, right? You should be able to take what's in the box and take the derivative. And if you did it right, the derivative of what's in that box should match where you started. Right? What's the derivative of x squared? 2x. What's the derivative of 3x of x cubed? 3x squared. Does it match? Absolutely. So you know you did it right. Is that cool? That's kind of nice. It's a very handy feature. You can't do that all the time, but with antiderivatives you can. All right, let's do the next one. Now the next one doesn't look quite right to be able to do with any of the rules that we have looked at so far. So I'm going to rewrite it to start with. How do you think it might be helpful to have this rewritten? Very good. X to the negative 6th, and I have that minus 2. Let me mention the dx on the end, actually, because I sort of glossed over that before, didn't say anything about it. Dx on the end, you need it, just like you need the plus c. Okay, so please use it every single time. These two things are attached together. They're like bookends. It's almost like the beginning of a parenthesis, the end of the parenthesis. Okay? They are attached together. The beginning part says, I want the antiderivative. That's that script S. The dx on the end says where x is the variable. That's what that dx means. It means the variable is x. And you guys know from doing related rates that the variable is not always x, right? You did some derivatives with respect to, say, t. Right? And for those of you who may end up in a class Calc 3 at some point, which I know is not everybody, but a couple of you might, you actually end up doing functions where you have more than one variable inside of there. And you need to know which one's the variable under consideration right now. So that dx on the end becomes even more important later on. So we're getting in the habit right now of putting that dx on everything, okay? Fabulous. Okay, so we've got that x to the 6th now. So what's the antiderivative of x to the 6th? What do I do with that negative 6?
You have 1.
I add 1. So what happens when I take negative 6 plus 1? I get negative 5. Now what? Divide by negative 5. Okay, so that's the first half. Now I need the antiderivative of the minus 2. We haven't done that one yet, right? What do I do with minus 2? I put an x with it, yeah. And again, if you're not sure, or if that feels a little funny, think about what happens when you try and take the derivative. What's the derivative of negative 2x? Negative 2. That puts us back where we were. I also need a plus c. All right, so this is finished in terms of the calculus that's involved. In terms of cleaning it up with the algebra, what do you think I might do to make this look nicer? Yes, Alexa, you're exactly right. The problem started out with a positive exponent and in a denominator. So the antiderivative also needs to look like it started out. Okay, so we're going to put it back down the denominator with a positive exponent of 5. Everybody good? Okay, let's try another one. Have 1 over x times the square root of x. Now what? I need to rewrite this first, actually. Let me put it underneath here. How might I be able to rewrite this in a more friendly way? Okay, you're exactly right, Josh, but now you get to explain why you came up with negative 3 halves.
So it's on the bottom because negative, and then you have the regular x, which is a power of 1, or 2 over 2, I guess, and then you have the radical x, which is 1/2, and put those together, it's 3 times.
Okay, is everybody with Josh on that? The x has a power of 1. Written in fractional form could be 2 over 2. The x that's underneath the square root would be x to the 1/2. And then he said, I don't know if you caught it, but he said it's negative because it's in the denominator, right? Okay, is everybody good with where that came from? Okay, good. Then we're able to use the antiderivative rules that we've already established. What do I have to do to that negative 3 halves? I need to add 1. So what would I get if I take negative 3 halves and I add 1? Negative 1/2. And then what do I need to do? Divide by negative 1/2, which really doesn't look friendly, right? I've got a fraction inside of a fraction. We will clean it up for our homework, but I need one more thing. Plus c. You guys are doing great. Okay, negative 1/2. What happens when you divide by negative 1/2? What is that the same as? Multiplying by the reciprocal, and the reciprocal of negative 1/2 would be negative 2. So I'm going to take a couple of steps to rewrite this. This would be the same as negative 2x to the negative 1/2. Is everybody good with that? Okay, but the problem did not start out with negative exponents or exponents that had 1/2 involved. So how would I rewrite this so that it mirrors how the problem started out? Good. Now, I want to pinpoint, plus C. I want to point out something that's a common mistake. Some people, and I know some of you guys did it too when we did derivative tests, want to like attach the negative 2 to the x value. It's not, right? So when I pull that x down to back to the denominator, the x to the negative 1/2 to the denominator, that 2 does not come with it, right? Negative 2 is a multiplication factor, so it needs to stay in the numerator where it was before. Okay, are we good? Does that one look okay? Excellent. Next problem. What is unique about this one? Here's multiplication, right? Now, you might have noticed we did not have any multiplication rules for antiderivatives yet. And we will barely touch on that in this chapter before this semester's over. The majority of what happens when multiplication is involved happens in Calc 2. That's a good thing because it's really complicated. How could I change this so there's not multiplication involved? I just multiply it out, right? And that's what we're going to do right now. We are going to multiply things out when we have the ability to do so because it simplifies everyone's life so much. All right, so let's multiply this out together. What do I get? Good? Okay. Okay. Okay, does everybody agree? Allison gave me those values. Everybody good with those values? Okay, before I go and take an antiderivative, I'm going to do one simple cleanup. What am I going to do? Yeah, we're going to combine those to be just x. If you didn't, it's not a big deal, but you'll combine them at some point later for the simplifying, so I feel like I might as well combine them now. Now we're ready to find an antiderivative. All right, so what's the antiderivative of 3x squared? Good, 3x cubed over 3. And there will come a point, and some of you may already be at that point, where you say 3x squared, its antiderivative is x cubed. You might start to see them. You will start to see them at some point. So at the point when you do, you don't need to necessarily write out the times 3 and the divided by 3 every time. That's fine, okay? But until you start to see them, please do write that out to keep your mind on track. All right, how about the x? X squared over 2, good. And then the minus 2? Minus 2x, and then plus c. There's really very little cleanup on this one, right? What's the only thing that needs to be done? The 3's. So if I were rewriting this cleaned up, it would look like x cubed plus, you could either write x squared over 2 or you could write 1/2 x squared. Doesn't matter. Minus your 2x and then plus c. All right, any questions on that one? So when there is multiplication, we're going to multiply. That's the rule of the thumb today, okay? Multiplication means just multiply and then do our derivative rules, antiderivative rules. All right, last one of this style is more interesting. Sorry, not the last one. There's 2 more on this one. The next one on this page is what I was looking at. Does your paper now say 1 minus cosecant x cotangent x, or does it have t's in it on your paper that you're looking at yourself right here? Number 5. Do you see x's in all the problem? Mm-hmm. Okay, good. I got them fixed. At one point, there were some t's lurking about, so I changed them. All right, so we have 1 minus cosecant x cotangent x. We're going to do this a piece at a time, okay? Start with the 1. What's the antiderivative of 1? It's 1x, okay? Or just x. What is the antiderivative of, in fact, I'm going to put the minus here for the moment. What is the antiderivative of cosecant x cotangent x? Yes, with a negative, right? So it's like this, and then plus the c. And again, if you recognized from the get-go that that negative was going to already be present and simplified, that's great. It's fine. But we have x minus, and then the antiderivative of cosecant cotangent is negative cosecant. So the only thing to simplify, if you hadn't done it while you were doing the problem already, is to recognize this would be x plus the cosecant of x plus c. Is everybody good with that? Okay. The next problem looks like what? Looks like a quotient, right? But there is no quotient rule for antiderivatives. Derivatives, yes. Antiderivatives, no. So we cannot try to do this as it's currently written quotient. We need some trig in order to change this expression to actually be something we can work with. Do you see something? It will be, you're right, Cooper, but what did you do before you got to there? Uh-huh. All right. Very good. Okay, so did anybody else notice that? The denominator is simply another way of writing cosine squared of x. It's actually squared too, isn't it? Okay, good. Let me switch my paper. Okay, is everybody good with that? Okay, that's a Pythagorean identity. Cosine squared plus sine squared equals 1. Okay, good. Now, there is a tangent involved there, but it isn't just tangent because that denominator is squared, right? So it might help for us to actually think of it written like this. this piece is tangent, sine over cosine's tangent, right? But this piece, which in essence really has a 1 above it, is 1 over the cosine. This is a reciprocal issue. So the first one we already identified, it's tangent. What is the simplification or the reciprocal, in this case actually the reciprocal of cosine? Secant. And if you're not remembering these, if it's been a while or whatever, I have a trig identity sheet online you can print out to remind yourself. Pythagorean identities, reciprocal identities, quotient identities. That's all the 3 you really need for what we're going to do in the class. But those 3 are important ones to use. They're going to simplify your life. Tangent secant, that's something we know. What's the antiderivative of tangent x, secant x? That is secant x. And then what do I need? Plus c. Now, I want to draw your attention to something that I've been doing, and I hope you've been doing it on your paper, but if you haven't, now's the time to fix it. Notice every single time I write the script s, I write the dx at the end. Did you guys do that? Good. All right, so every single time I'm doing a rewriting step, I'm rewriting both of these because that signifies I haven't yet done the calculus. All I did was algebra inside of the antiderivative notation. Okay? Kind of like when we were doing limit. We wrote limit on every single step until we actually plugged whatever number it was in for the variable. Right? Same thing. Okay? I have one more problem. Any questions on what we did so far? Okay, let's do the one more problem. This one says, find the function f of x satisfying the given condition. This is the place where we're going to figure out what c is for this particular problem. All right, so before we do that, we're actually going to find the general antiderivative. That is, we're going to find, whoops, and it's actually little f of x here now. The reason is because this is actually notation that says f prime. Right, it already starts out f prime, so all I have to do is become f to get the value 1 back from that, to take the antiderivative 1 back from that. If it had started out as f of x on the left-hand side, then that's when I would put a capital F to give that notation. All right, 12x squared. What's the antiderivative of 12x squared? 12x cubed over 3. What's the antiderivative of plus 2? Right, I've got my plus and then 2x. And then I also need plus c. Let's clean this up. What happens to the 12x cubed over 3? 4x cubed plus 2x plus c. And if I was not given this piece of information, I would be done. There would be nothing else I could do. How could I use that piece of information, though, that's highlighted in blue, to figure out what c is?
Set the equation equal to 2, plug in 1 for audiences, and solve for c.
Okay, so this is what Allison told me to do. She told me to put the 2 in on the left-hand side, because that's the function value, right? It says it over here. That function value is 2. And then put the 1 in everywhere I had an x, which I can do that. And then the only thing left that I don't know is c. Right? So what does this really do physically? Well, I did an antiderivative, which means I've got a shape of a graph. The plus c means it can be shifted up and down at any level from there. But once they give me a specific point, it fixates the problem, right? It fixes it in a specific place. I can't move it anymore. It means I actually have the ability to find out what that plus c is because the graph is now fixed by knowing 1 point on the graph. All right, so let's figure out what is c. There's 2 on the left. What do I have on the right with 4 times 1 cubed plus 2 times 1? 6 plus c. So what is c? It is -4. Now, be careful to not think that you finished the problem. The problem actually asked us to find f of x. So we actually need to state what is f of x. So what is f of x? 4x cubed, and then what? Plus 2x, and then minus the 4. So you've got this very last piece at the very end that allows us to find c. These problems are often called initial conditions, and initial doesn't mean first, really. It just means that we're given some piece of information that allows us to fix that value and to solve for c. It's an initial condition problem.